Hello, everyone. Let's talk. Let's keep talking, guys. On one of the videos, a couple of the problems, or at least one of the problems, the audio cut out. Largely my fault. I wasn't careful with how much battery life I had in the microphone. So I don't think it's an issue. I think you'll be able to see the lion's share of everything that I wanted to do, and it's also in Canvas as well. But so it's also posted for you. But I think you can, even with what's up there, the lion's share of what I'm doing, if not all of it, you'll be able to follow it anyway. But just in case, I want to give you a little more continuous audio for problems 65 and 66 from chapter 18 from the Katz book. A number of problems were already covered from that chapter, and overwhelming majority of what's being covered should be very clear. But for these two, I think the audio cut for about 5 minutes out of a 2 hour 20-minute video. About 5 minutes of audio were apparently lost because, again, I had to replace batteries and stuff. So don't think you really need it, but in case you do, let's do it anyway. Problem number 65 from chapter 18 from the Katz book. They got two wave functions, y1 and y2, given as follows right here. And those two wave functions describe two sinusoidal waves traveling on the same string, where x, y1, and y2 are in meters and t is in seconds. What are the A, B, C of the following? The A, the amplitude. What are the amplitude? That's A. B, what is the frequency? C, the wavelength of the resultant wave. So they want the amplitude, the frequency, and the wavelength of the resultant wave. That's A, B, C. Well, look, guys, I'm pretty sure everything's okay just as it was before, but let's just do this anyway to cover ourselves to be okay on this thing. We know that if you add two sine functions, sine of alpha plus sine of beta. If you were to add two sine functions, sine of alpha plus sine of beta, it's going to be 2 times the sine of the quantity, 1/2 of the quantity alpha plus beta, times the cosine of the quantity 1/2 times the quantity alpha minus beta. Alpha and beta can be anything that are valid in the real numbers using radians for this thing to work out for us. We can convert things from radians to revolutions to degrees, so that's not going to be an issue. Right now, let's say with the radians, you know the radian is very, very significant in its association with the real number system and in association with the measuring stick that occurs on the number line from 0 to 1. The radian is scaled to that phenomenon, to that reality. The radian is scaled to that better than any other measuring stick that we have. Better than the degree, better than the revolution. We can still make everything work out if we play it right without great difficulty, but again, the radian's really, really good for doing this sort of thing for the aforementioned reasons that I've brought up a number of times. E to the I theta equals cosine theta plus I sine theta is a very good way, to start to look to remember. This beautiful mathematical formula, e to the I theta equals cosine theta plus I sine theta, helps us manipulate a lot of stuff and get a lot of answers. It helps us arrive at these conclusions, actually, to be honest with you. We know that. We've talked about that. Let's call alpha kx minus omega t plus pi over 2, and let's call beta kx minus omega t, that's it, nothing else, plus 0. So beta is kx minus omega t, alpha is kx minus omega t, also plus pi over 2, which is not before. So here's alpha, here's beta. They gave the wave function y1 equal to the following right here. They gave the wave function y2 equal to this right here. This is why I have alpha is kx minus omega t plus pi over 2. Alpha is kx minus omega t plus pi over 2. And beta is kx minus omega t. That's it. So here's your beta, here's your alpha. Many ways to go here, guys. As we look at this, How do we do it? Well, I'll remember that this is the truth regarding this. This 3 and this 3 right here, they're the same, which is very fortuitous. There's ways we can do many things in mathematics. The mathematics does indeed get easier for this particular problem when the initial amplitudes under consideration are the same for both wave functions. We can factor them out when we do any kind of addition. They don't play into it, and we'll just do this. There's like a capital A in front of this guy, a capital A in front of this guy. So if it's A sine alpha plus A sine beta, say, well, wait a minute, you never gave me a formula like that. I don't have to. I can pull an A out of there, and there you go. I did give you this formula. Sine alpha plus sine beta is something. At the end of the day, you just multiply it by A, and you can deal with it. So, okay. That's pretty important stuff in that regard. So they made it pretty easy for us that way. Here it is. When you take and it's going to be double what this guy is. So here's what you do. Since the 3 is common to both, bring the 3 out, or have the 3 somewhere, and when you add the 2, what happens is you double. Okay, so I'll double the sign. Oh yeah, and there was the 3 on the outside. So if the 3's on the outside, 3 times 2, that's going to be 6. When you deal with the sign, you're going to deal with alpha and beta added together, then get half of it. Well, let's be careful. This and this added together are just double what this is, and if you take half of it, you just got this. The 2.00 pi x minus 15.0 pi t. Great. Oh yeah, but there was a pi over 2. Divide the pi over 2 by 2, or multiply by a half, you get pi over 4. There's your pi over 4. There's this right here, times the cosine of this. What's going on? Take this, minus that. All of this takes away all of that, and you got pi over 2. Then it's just, forgive me, yeah, it's pi over 2. So basically it's this. It's all of this minus all of that. This part and that part go. You got pi over 2. What's half of pi over 2? Pi over 4. So we come to here. The cosine of pi over 4, pi radians is equivalent to 180 degrees. 180 degrees divided by 4 is 45 degrees. The cosine of 45 degrees is the square root of 2 over 2, about 0.707. 0.707 times 3 times 2 is going to get you, at the end of the day, 4.24, roughly. So pi over 4 radians, the cosine of pi over 4 radians is the square root of 2 over 2. Put that right, you pick that up, put it right here. Go 2 times square root of 2 over 2 times 3. Well, that's just square root of 2 times 3, whatever that's going to be. That's 4.24. Now you got the sine of all of this. In my notes, I had the sign here, you guys, as pi over 4. I had it as pi over 2, rather. That was a mistake in the notes there, so be aware of that. This is the way it should be, because remember, it was pi over 4 when we did everything that we had to do. Okay? So, that is it. This is kind of the whole thing. What does that mean? Well, that means that this thing right here is the amplitude, and I can tinker with all the rest of the stuff and get the answer that I need to get. That should be pretty straightforward stuff, guys. As I said, the way it was done the first time, when there's a whole bunch of other stuff that I was doing, other problems that I was doing, overwhelming majority of that was fine. Later on with the audio having a little bit of an issue for just a short period of time, I think you would have gotten through it anyway. But I think this is a good idea to do this anyway, just in case. Cover all the possibilities that could happen there. This is 4.24 for the amplitude, guys. They're using meters, they're using seconds, they're using the whole thing here. This is 4.24 meters for the amplitude. Amplitude, or Y max, or whatever you want to call it, is 4.24 meters. Okay, good enough. Now what? At that point, guys, we tinker with this a little bit, and we should be okay. What about the frequency regarding this thing? Well, again, guys, you got to look at this whole thing. This part right here, I almost don't want to write on it. You know, maybe I should go up here. It's really the same thing as that, just not fully worked out right here. But this right here is your K. 2 times pi is the K. And the 15 pi is the omega. So let's tinker with that. I mean, they gave us that much. The 15 pi is the omega. So what's going on here? Well, let's do a couple things. Omega, they want the frequency, right? Omega is 2 pi over capital T. 2 pi over the period is equal to omega. Omega is also equal to 2 pi times f. If you divide by 2 pi on each side, f equals omega over 2 pi. Sounds good to me. What do we say it was? Well, we said, guys, just match it up. This is some kind of a kx. This is k times x. This is omega times t. This is omega times t. So 15.0 times pi, or just 15 times pi. You guys know where this is going, guys. At the end of the day, that's 7.5 hertz for that. Okay? That's B. See where C is going to go on that, guys. C, they want to know what lambda is. Then we say that K was equal to 2 pi over lambda. If you multiply by lambda on each side, divide by K, 2 pi is 2 pi. What's K? Well, how do they write K? That's 2 times pi. 2.0 times pi. That's 2.0 times pi. That's the K. 2 pi divided by 2 pi. And that was it. Like I said, guys, I'm pretty confident. I don't need to do this again, but I am doing it again. I'm pretty confident we don't need to. But what the heck? I think it's just repetition. Repetition is the mother of learning. I remember there was a Russian professor I had, Russian TA, said, "Повторение мать учения." Repetition is the mother of learning. So sometimes you look at this stuff again, it's not bad. So that's it. That's the three, you guys. Amplitude, frequency, and wavelength. Very, very interesting. What's going on here? What's going on here, I think of significance for us to kind of look at is, if you look at what lambda, and we can kind of mention this as we go with the other one too. If we look at lambda, if we look at the frequency, and if we look at the amplitude, well, amplitude's pretty straightforward. You do the mathematics, whatever's on the front end of that whole thing, that's the amplitude, and that tells you a lot. And it has a lot to do with the amount of energy that is required. If you want to do something with a particular amount of frequency, with a lot of frequency, and you want it, the wave, you're trying to judge here, hey, what kind of power output is this wave bringing forth? There's a lot you can say. Well, what comes into play? Omega plays a big role in that whole process. So does amplitude. If you're making this thing travel in the let's talk about a transverse wave. In the transverse direction to the propagation, if this thing is oscillating up and down tremendously, you need a tremendous amount of energy over a particular period of time for that to be accomplished. You need less energy if the amplitude is not as prominent. The amplitude is not as prominent. So you know that. What about this? Well, omega and F, I told you, are very closely related to each other, directly related to each other. They are directly proportional. If omega is made 10 times bigger than it was earlier, if it's made 10 times the size of what it was earlier, then the frequency will be made 10 times the size of what it was earlier. If you make omega 1/10 of what it was earlier, the frequency f will also be 1/10 of what it was earlier. So we talked about that. Regarding this, what about lambda? You get a long lambda if k is a big number. You get a short lambda if k, forgive me, let me take that back. I said that wrong. You get a long lambda if k is a small number. If k is a small number, a constant divided by a small number is a big number. So if k is small, lambda is going to be big. If k is big, lambda is going to be small. So here it's different from the frequency and angular frequency, f and omega. Here it's different. F and omega are directly proportional to each other. Lambda and k are inversely proportional to each other. A large k is indicative of a short wavelength. A small k is indicative of a long wavelength. It's pretty interesting stuff in its own right. As we look at that, how would you explain that? Well, I'd explain it looking right here. Here's the k. For this thing to cycle, it's going to cycle every 2 pi. If this is a big number, you don't need a lot of x displacement from 0 to something, which would give you the lambda. You don't need a big number x for you to go one full cycle if this is really big. If this is really small, you do need a lot of x for this thing to do a whole cycle. So this thing will cycle as rapidly, if you allow me to say that. I'm not entirely comfortable even saying it that way, but for our language, just this thing will cycle quite a bit. We'll do a full cycle in a short amount of x if this k right here is a big number. This k right here is a big number. You don't need x to be a big number for this thing to do a full cycle, to do a whole wavelength. If this is big, x can be small. X is associated with the wavelength. Likewise, if this is small, you need a lot of x for that to happen. And that's a big wavelength for the wave number there. All right, that's 65. I think that was the one that I was told was a little bit of an issue. But let me do 66 just to be safe as well, you guys, as we talk about this. It's a very, very similar argument, 66 as 65 is. So let me kind of run through it somewhat quickly. Okay. All right, guys. Be aware. Right, just be aware of the notes there. There's a pi over 2 at the very end, and there should not be. It should be a pi over 4, and that's why I've corrected right here. So be aware of that in case something happens. When you see it and you're confused, there's a reason for it. I had written it down initially incorrectly. That's the way it should go. Okay. All right, guys, same exact argument in numerous regards for problem number 66 compared to what I did for problem number 65. It's like the same kind of look happening there. So let's kind of like jump to it really quickly and just have this done for you guys when we look at it. They're asking, they're making this look. In fact, how do they even say this? Right, they're saying essentially, let me write it down here and we'll get to it. It's very much the same kind of argument that took place in 65, guys. So let's not kind of problem number 65. So say if I'm going to add, so we know a lot. You just saw it, so we'll leave those notes as is. And those notes were good, the initial stuff they told us how to do some of this stuff. They're telling us that y1, and here's what kind of saves the day on this one. They're telling us y1 is equal to an amplitude of this much times the sine of 0.350 pi x minus pi over 2t. Okay, they're doing that. This one's actually somewhat easier to look at. This one's going to produce a standing wave. So the other one did not. Well, this is important. I guess it's something to say. If you go back to problem 65, you saw the solution that we got, and we said a number of things there. That problem did not yield a standing wave because it didn't meet the criteria for a standing wave. It was a traveling wave, and it wasn't bounded in a sense going back and forth in a standing wave pattern. The mathematics wasn't indicating that. Here the mathematics will indicate that this other problem is indeed indicative of a standing wave taking place. Whereas with the other problem, problem 65, that was not the case. Okay, something to be mentioned. We do find ourselves in a fortunate situation, as we did with number 65, that these two amplitudes were the same, so that wasn't too big of a difficulty for us to do some of this stuff. So there it is. I mean, they tell us now, we remember y of x comma t. Y of x comma t sine kx. Okay. Well, let's talk a little bit. I mean, there's a little bit of talking we got to do, I think. Here, it's going to come down to here. Now you're saying, oh, wait a minute, yeah, where are you coming from? I'm telling you it's going to come to here. At the end of the day, it's going to come right to here, ladies and gentlemen. It didn't do that for problem 65. I already told you that. It was not a standing wave for problem number 65. The mathematics did not yield this. The mathematics did not yield, hey, it's only a kx, it's only an x that's variable in this product. It's only a kx, and well, let me say it again. We have a product here. In this factor, only the x is variable, and in this other factor, only the t is variable. That didn't happen with problem 65 because it was not a standing wave, but it will happen here. It will happen here. And the reason for that, I mean, it'll come down to here. Now before we get to there, let's talk about why it comes down to there. If you have this right here, let me leave that for now. Let me just leave that there. 2 y max. Y max is the same as capital A, amplitude. So we're not going to have too much of an issue there. Sine 1/2 alpha, and this is what does it. And this is what makes it happen, you guys. Well, yeah, this should look very repetitive because we just saw this. Yeah, we just saw this. We just didn't see that conclusion for problem 65. We didn't see that conclusion because the mathematics didn't yield that conclusion. The mathematics not yielding that conclusion means that it's not a standing wave. When it does yield this conclusion, and it will for problem 66 that we're on right now, it will yield this, that's a standing wave. Let's talk about it. Well, this is the thing. It's a number of ways to do this. I don't want to get too crazy with it, but we can just say this. We can say that alpha is going to be kx plus omega t, and beta is going to be kx minus omega t. Could you have written those differently and still gotten the same answer? Yes. The only thing that's going to be altered is the cosine. It's going to be cosine of negative omega t. Yeah, but the cosine of negative theta equals the cosine of positive theta. So that wouldn't change anything. Make a long story short, you can label them any way you want. Be consistent. It's still going to yield the mathematics, provided we know what we're talking about. Provided that we know what we're doing and we're careful. What's going on here? Well, let's do it. Here's alpha, here's beta. Add them together. Omega t and negative omega t is 0. Kx and kx is 2kx. Omega t and negative omega t is 0, as we said. So the kx and the kx is 2kx. Half of 2kx is kx. There it is. There it is. Half of 2kx is kx, and that's this right here. That's where they're getting that. Alpha minus beta, kx plus omega t minus kx minus omega t. The quantity kx plus omega t minus the quantity kx minus omega t. Kx minus kx is 0. Omega t minus a negative omega t is plus omega t. Omega t and omega t is 2 omega t. 2 omega t, half of 2 omega t is omega t. If you'd have gone the other way, take this and subtract that from it, you get negative 2 omega t. Divide by 2 or multiply by a half, that's negative omega t. Cosine negative omega t and cosine positive omega t are identical. They're equal. And we can look at that, how it's actually graphed for the cosine function. The cosine function has symmetry. So what happens here is going to happen there. What happens here is going to happen there. There's symmetry all over the place. There's symmetry with the sine function, but it's anti-symmetrical. It's odd. It's odd symmetrical. This is even symmetrical, I guess you could say. But there's a lot of symmetry throughout the trigonometry. Okay. Okay. We got what we got. We said this kind of runs the show, and we get down, bam, to there. The rest is just plug in the numbers. Now we said we lucked out. This guy, you're going to have a much different dynamic to deal with if the amplitude's off. I mean, there's stuff we can do. We could certainly figure out what we could do, but that's neither here nor there. Let's not approach that. There's ways you can add all sorts of trigonometric functions that don't look initially that they're behaving very well for us, and we can still figure out a way to say something here. When they're I'll leave that. I'm going to leave that as is for now, you guys. So let's leave that, and that's another interesting matter that we can explore, I guess you could say, as the time would, if the time ever arose for that. Right now, we don't need to. We have this. We got what we need, and what are you going to say about it? Well, you've got y of x comma t. Now we said you saw what I did for problem number 65, guys. Let me just do it again. Let me factor the 2.40 out of there times 2 times, and now let's see what we got here. Be careful. Who's who? Well, here's your kx. There's the kx. And here's the cosine. And what do we say here? Cosine pi over 2 t. Yeah, the 2 should have been out here maybe, whatever. The 2 is eventually there. This is what we're talking about, the 2y max. You had a y max. This was your initial y max, 1.20. 1.20. And you can, like I said, you can bring that thing out of there. Now, they're essentially, it's good enough. I mean, that's good enough for us, guys. We're there. We have what we have. When you double that, you get 4 point, no, it's not good enough, actually. It should have been the 2 times the y max. So the 2 times the y max. Forgive me. Right there, guys. That should be right there. Okay? 2 times 1.20. And when you double that, yeah, that's where you're getting this. And no twos, no anything here. 2.40. You got this right here. It's written in a number of ways. I think the other time I did it, I might have used a slightly different look to it, but it's the same exact thing, guys. Should be pretty obvious. Is this believable? Yeah, it's believable. Pi over 2t is omega t. 0.350 pi x is kx. Okay, that's where everybody... 0.350 pi x is kx. Pi over 2t is omega t. Sounds good to me. There's a lot going on there, guys. So what do you want to say? What do we want to say to talk about it? This is a standing wave. Here's why it's a standing wave. It's not really moving. Tough way to say this. It's not moving very far to your right or to your left. It's staying in one place, going back and forth. We'll call that a standing wave. It is. So it's not going very far to it's not going far to your right indefinitely, and it's not going far to your left indefinitely. It's staying between confined limits. Well, how do I know that? The mathematics tells you a lot. This thing right here, as we proceed with this, will give you some sort of idea of what's happening here. In other words, as time goes on, we have oscillation going on here, guys. Back and forth of where it is. So for a particular value, as we look at this thing, it's not going to be moving. So we know that within particular limits of what's happening here, once you pick a value of x, that value of x, oh, see, this is I guess what kind of clinches the whole thing. This thing right here, with the passage of time, and you can almost imagine some sort of imaginary distance being covered when it's not being covered, but it just is going back and forth. The real big thing here, guys, is that the biggest value that you could have for the sine function is if what's inside the argument of the sine function were pi over 2. Or something that would give you the sign that pi over 2 would give. You know? As far as the biggest magnitude that you're going to get there. If this whole thing is pi over 2, the sine of pi over 2 radians is 1. Anything other than that doesn't give you the same value is going to give you a smaller number. Once you plug in here anything, where does the sine function go, guys? The sine function goes anywhere from -1 to +1, including -1 and +1, and all real numbers in between. Once you lock into a particular value, you're only going to oscillate. Let's say I get a sine here and the sine's not 1. The sine of the theta that I have here, the sine of what's in the argument, is not 1, but it's equal to 1/4. Well, if that were the case, let me just kind of make something up here, guys. If this were and then bouncing, coming back as time proceeds, once you get a particular value, the cosine of this will make it oscillate up and down. Once you get to the big value of 1, it'll oscillate up and down. Here, it'll oscillate up and down, but it'll never, right here, you guys, this will never climb to where this is. This will never climb to where that is, nor will this guy climb as low as that guy, or this guy climb. They're just, it's stationary in a sense. In a sense. I don't want to, there's a lot to be said here. But we know once this guy locks into a value, for a particular value of x, you pick that value of x that you want from, the length of the string. The length of the string under consider, for example, let's say length of the string or whatever length we're talking about. Capital L. get all the values of x that could take place there. Once you lock into a value, wherever it might be, I mean, here you got this, you got that. Here, this is the biggest value, and that's the biggest magnitude value in the negative direction. This ain't getting as big as that, and this one ain't getting as big as that. They're kind of stuck. They're just, and this kind of is an indication of that. That's an indication of that. So, again, whereas you look at waves that travel, everybody on the rope is going to eventually, though later, some earlier, everybody is going to hit the maximum value and come all the way down to the minimum value. And then later on, boom, the wave's going to go through and it's going to happen again with a period of capital T. With a period, after a period of capital T, it will take a period of capital T to do the whole cycle. Every time the wave comes through, depending on the wavelength, depending upon the frequency, but every single point on that rope is going to cover the maximum sign value, the minimum sign value, from 1 to -1, from -1 to 1. It's going to oscillate all of them. This won't cover. This covers from -1 to 1, but that don't. And it's never going to do it. But a traveling wave, every single one of these is going to hit the full amplitude eventually. It's a big thing. It's a big thing. So if that's the case, they gave us this value, and then they're saying, okay, let's solve it from there. So I guess that was something I wanted to say a little extra regarding that. Since we went this far to actually look at these two problems again, I think that's worth talking about a little bit. Okay, so we're looking at that, and I'm not saying it's got two bulbs like that where the nodes are set up like that. There's 3 nodes, like far end, there was the far edge, the other far edge, and the middle one. I don't know how this, we'll look at it. We'll see where it's at as they ask us to do problems like this. But anyway, this is how it's looking. So they're asking 2 questions here. Forgive me, they're asking 3 questions here, A, B, C. They're saying, given these wave functions, they describe 2 transverse sinusoidal waves traveling along a rope where x and y are in meters and t is in seconds. Okay. What is the maximum transverse displacement of a rope element located at A equals x? What is the maximum transverse displacement of a rope element located at part A now, question A, x equals 1 meter, and B at x equals 3 meters. C, where are the first 3 antinodes located along the rope? Nodes are at the bottom, are like kind of like at ground zero, and antinodes are at the very top. So where is it located? Where are the first 3 antinodes located along the rope? At what value of x? And what is the maximum transverse displacement when x is equal to 1 meter and x equals 3 meters? Okay, so that's essentially what they're doing, guys. It should go pretty straightforward. See what we can say here. All right, well, for both A and B, cosine has to be a maximum value. Look, guys, for A and B, they're saying, give me, how am I ever going to get a maximum value here? The cosine function has to be a maximum for me to get a max value over here. Well, okay, there is a place where it's at a maximum. I mean, we could figure that out. If t is equal to 0, if t is equal to 0, 0 times pi over 2 is 0. The cosine of 0 is 1. That's as big as the cosine function gets. Do you want to go, and from there you can even get a -1 out of there. If the oscillations, well, they're not really going there. There's ways this can be played. Even with the negative one, a negative one times a negative number would give you a big positive answer as well. They're not going in that direction from what I'm seeing here, so we're not gonna go there either. T equals 0 sounds good to me, and there's other t's where this will happen, and we'll talk about it. We'll talk about where this could actually take place. You could. Some very interesting stuff. Very interesting mathematical arguments you could make here. They're not going there, so I'm not going to go there. I think the best way is I'm going to leave this as is, and let's see what they have to say here. If the cosine of the quantity pi over 2 times t, the cosine of the quantity pi over 2 times t is equal to 1, then we're looking at a situation where just this guy, in those circumstances, and we could play this all day. I mean, so we got this right here, sine, wherever that's going to be, sine of, and they said 1, right? If x is equal to 1, then you got 0.350 pi. Make sure you're using radians on your calculator if they're giving you radians. Do you want to convert the radians to degrees? You could do that too, and then use degrees when you're trying to calculate what's going on. 180 divided by pi will give you degrees. 180 divided by pi, you got 180 divided by, you could wherever you see this, just multiply this by 180 divided by pi. That's the pi's cancel. You got 180 times this. It's going to be 3.5 times 18. It's going to be 54. It's going to be like 64 degrees if I'm looking at it right. 0.35 times 180. Let me just think about it. Yeah, it'd be 0.35 times 180 is 3.5 times 18. 3 times 18 is 54, and half of 18 is 9. Be 63. So 9 and 54, 60. The sine of 63 degrees will give you an answer. You multiply it by 2.40 and you get it there, or leave it in radians, you're going to get it there. All right, guys, to make a long story short, let's just get the answer. For A, the maximum value attainable is 2.14 meters. If you're located at x equals 1. Is that as big as the amplitude? No, it ain't. We know how big the amplitude is. We already discussed that. The amplitude is 2.40. That one ain't allowed to get there. It ain't going to get there. You can't do it. It will somewhere. Where would that happen? Where would that happen, huh? Well, this guy's already out of the picture. For this situation right here that we're in, we just set the whole thing equal to 1, and then we're not going to worry about it too much. There's probably a number of ways you could argue this. You could say if you're going in the opposite direction, how this stuff works out. That's another story. Okay, but quite interesting. There's a lot can be said here, guys. So if we looked at this, that would be where it would be if it was for 1. For x, put a 1 right here, and what we got for an answer. True. Let's talk about what it would be at 3. Likewise for 3, at x equals 3, y would be equal to what? Well, here was x equals 1. Here was x equals 1, and we did all the monkey business and got the answer. All right, so let's see. So that was x equals 1, you guys. And we saw that. Okay. Now, put 3 right there. What's that all about? Well, let's see what it's about. 3 times 0.350 is 1.05. 1.05 times pi, 1.05 times pi radians. The sine of that will give you what you want. You multiply it by 2.40. Remember now, when we put the 1 in here, we ground out the answer and we multiplied by 2.40. And we got for A, for x equals 1, 2.14 1.04 meters. What's going to happen here with the 3? It's 1.05 times pi. The conversion would be 180 over pi, so it's 180 times 1.05. How is that all going to play out, right? It's like, I think it's like 100. I'll tell you exactly how it come out. It'd be 189 degrees in degrees. Give me the sine of 189 degrees. It can't be that big. Certainly cannot be that big, and in fact, it's a negative number. But so it's going to be whatever that's going to be. It's going to be a negative number times this. Really not that big, which makes sense. It's close to 180. It shouldn't be that big, as we're looking at it. So you plug that in there, and again, guys, you're multiplying by 1. In all instances here, this guy was 1. So you're multiplying by 1 in all instances here. When you had put the 1 right here in the argument, you ground it out. You multiply by 2.40, you got 2.14 meters. Here you plug in the 3, grind the whole thing out. Again, you're assuming a 1 for whatever reason, right? Because you're looking for the maximum. And you're getting an answer here of negative 0.375 meters. Yeah, true, but so that's not the maximum displacement. The maximum displacement is the absolute value of that. So this is really what you're looking at. For that one, the maximum displacement is going to be the absolute value of that y. And this is what they want. This is where the maximum is going to be. They want a positive number there, and they gave you that answer. Okay. That's B. C, antinodes are places of maximum displacement. Once again, ladies and gentlemen, we're going to set the cosine of pi over 2 times t to be equal to 1 to get the maximum displacement. So it's going to be equal to 1 in this instance as well. And now you're going to try to find out where it's going to happen. You need to find, so now you got to be now we got to be a little on the careful side. This negative right here that we got was sort of a precursor of what we need to be looking at. So antinodes are places of maximum displacement. We are going to say that since this guy is equal to 1, let's make that, since that guy is equal to 1, you guys, this has got to meet its maximum value if that's going to happen. And for that to happen, this right here has to meet its maximum value. So to kind of make the long story short, we set the cosine of pi over 2t equal to 1, though negative 1 also works if things are done correctly. Let's not go there. Again, I'm sort of arguing this whole thing with myself, where to go there with you on this. For now, let's just say you got this. Yeah, that's going to make it. If I can somehow find a place where it's plus or minus the maximum displacement, if I can find a place where it's an x value that gives me a plus or minus 1, I'm okay. If I can get a plus or minus, I got to find an x that'll give me a plus or minus 1. Now, what are we talking about? Well, I mean, the way that works is pi over 2 will give you a positive 1. If you go another pi units away, 3/2 pi will give you a negative 1. If you go another pi units away, 5/2 pi will give you. So, I mean, look, I'll make a long story short. The sign is going to give me plus or minus 1 at pi over 2, at pi over 2 plus pi, and at pi over 2 plus pi plus pi. What do I mean? I mean that at 1/2 pi, it's going to give me a maximum displacement, either in the positive or negative direction. The sign of the following three quantities will give me the first three antinodes. The sign of pi over 2 will give me a maximum displacement that is present associated with the sine function. The sign of pi over 2 will do it. The sign of pi over 2 plus pi, which is equal to 3/2 pi, will also give me a maximum displacement. And the sign of pi over 2 plus pi plus another pi, plus 2 pi total, which is 5/2 pi. Look. Yeah, true. Theta has got to be pi over 2. Let's say theta 1, if you allow me to say it. Theta 2 is going to be 3/2 pi. Yeah, not so fast. This is true. This is true. But they gave you a whole big mess right here that you got to make that look like this. In other words, you got to make this guy 0.350 or 0.35, if you allow me to say it, pi is going to be equal to x. You're going to make the 0.35 pi x equal to that guy. You're going to make that guy look like, there's going to be different x's here. There's going to be x1, x2, x3. And that's the big one. That's the trick. That's the trick in this whole thing. Okay? So this guy right here is going to equal all that. This guy right here is going to equal all that. And this guy right here is going to equal all that. Yeah. Solve it. Solve it. And once again, solve it. Figure where it's at. Shouldn't be too bad. The way it's playing, so see exactly, I wrote it a little bit differently. I mean, when I first, in the notes here, guys, and I think we're going to see in the other one, you're going to see I went like this. I went 0.305, point 0.350 pi x is equal to n times pi over 2, but you got to skip with that. I mean, it's got to be where x, forgive me, where n is 1, and then you add pi over 2 plus pi over 2. You're adding pi's to it each time. Well, to add pi's, you got to take the original, then add double what the original was, so you're adding 3. Take this one, add double what the original one was, so 2 and 3 is 5, ... This is the way it's going to work. It's 1, 3, 5. It's the same thing I just talked about if you deal with it. What do I mean? Here's a 1. Here's a 1, here's pi over 2. 1 times pi over 2 is pi over 2. 3 times pi over 2 is 3/2 pi. 5 times pi over 2 is 5/2 pi. So it's the same thing. The rest is math, guys. The rest is just the numbers that you're knocking out there. Let me solve x1, x2, and let's see what we got here. And the way it came out, let me solve for x1. Let me solve for x1. Let me divide by 0.35 pi on each side. And it's pi over 0.7. Forgive me, no, it's not. Let me divide by 0.35 pi on each side to get x1. Get x1 all by itself. Divide by 0.35 pi on each side. The pi's cancel, and you got 1 over, you basically got, I mean, let's go with this. This is 1 over 0.7, and we'll cross that bridge in a little bit. Then the other one, x2, and I wrote it a little bit differently in my notes and in the other video. So it's up to you how you want to look at it. Either one's fine. Just make sure you get it. You can write this stuff in a lot of different ways. So I wrote a little differently in my notes, and in the other video I wrote it a little differently, but it's the same answer in the end. Divide by 0.35 pi to get x2 by itself. Divide by 0.35 pi on each side. Well, the pi, when you divide by 0.35 pi on each side, the pi's cancel, and what you got here is 3 over 0.7. I'm certainly not done, guys. I mean, I'm just trying to kind of hit this a little bit and see what we can do. Divide by 0.35 pi on each side here to get the other one, and that's 5 over 0.7. Okay, sounds good. So what do you want to say about it? Well, I mean, might as well get an answer for it at the end of the day. So for C, you guys, let's just kind of talk about, let's kind of grind it out. There's the x1, the x2, and the x3. I labeled them, like I said, in the other video I labeled it a little bit differently, and in the notes it's labeled differently, but that's not a big deal. The first 3 nodes, and again, what's 1 divided by 0.7? It's roughly 1.43, and it's in meters. What's 3 divided by 0.7? That's 4.29 meters. What's 5 divided by 0.7? 7.14 meters. And that's it, you guys. And that is what they're talking about on all of these. That's x3, that's x2, that's x1. Where's it going to happen? These nodes tell you a lot, you know. Now you got to remember there's antinodes there. So I think if you're gonna actually find the wavelength, this is where it can get a little. You got to watch out now. So, oh, hey, you said node to node, node to node. If I go from a low place to another low place, it must be a wavelength. No, the cycle repeats, but it's, you know, you got to remember these things show up twice sometimes in the full cycle. So you got to watch that. This guy happened, you know, this guy's gonna bring them down to a negative place. This guy's going to bring them down to a positive place again. This is the full wavelength, ladies and gentlemen. This is the full wavelength, indicative of an entire cycle having taken place. There's 2 pi between the 2 thetas. When there's 2 pi between the 2 thetas, from those 2 locations, you can find the wavelength. When there's an entire cycle that has taken place, that means a whole period has transpired. This is just half a period, you guys. The difference between these 2 is pi. Yeah, pi degrees happens in half a period. 2 pi degrees, 2 pi radians, forgive me, pi radians happens in half a period. 2 pi radians happens in a full period. Here's your wavelength between these 2. What does that mean? It means this. Take 7.14 and subtract 1.43. That's your period. That's the full period, and then that's your wavelength. That's your full period that took place that we're looking at with this this function. That's the whole period that took place. Now what's the wave? This is only half a wavelength. What do you mean half a wavelength? I mean this difference right here is half as big as this difference. I'll put it another way. 4.29 minus 1.43, that's equal to I want to think 2.86. Let me just kind of argue with myself on that. .83 maybe, roughly. I mean, the thing is, there's been a round off, guys. I think it's like 2.86. This is half a wavelength. In other words, from here to here, it's let me just look at it really quickly. 2.86, roughly. Again, I did a round off, guys, so let's not be too, Here's the round off. This is 2.86 is half a wavelength. This should also be 2.86. It's not quite, because I rounded off. But the distance from here to here is 2.86. And let's make sure that's right. That's correct, 2.86. And the distance from here to here is also almost 2.86. It's going to be 2.8. Let's see here what it got. Let's add it. The distance here, 2.85 on this one. So this is 2.85 distance. This is 2.86 distance. They both should be about 2.86 for half a wavelength. If you add them together, you should get 5.72 or thereabouts. Nobody asked you the wavelength of this standing wave, but it's 5.72. What is that? It's 7.14 minus 1.43. I said that's going to be well, according to this, it's coming out about 5.81. Let me see here. I said 5.71, the distance between these two. If you do these two subtractions here, get a better answer maybe. 5 over 0.7 minus 1 over 0.7. 5 over 0.7 minus 1 over 0.7 is 4 over 0.7. Nobody asked you this, but I tell you, it's not a bad question to ask. Nothing wrong with not having asked that, certainly. They ask a lot of great questions here, but this is certainly a question you could ask. Okay, by the way, what is the wavelength of this thing? What's going on here? What is the wavelength of the standing wave? Well, I'm saying it's 4 over 0.7. We're thinking it's 5.72. Again, I'm doing this kind of on the fly, guys, but it's good mathematics for us to be looking at it, I think. I got 5.714285714. So 5.714 thereabouts. .714 meters. I told you it was going to be the ballpark of 5.71, 5.72. Remember, guys, I rounded off. These should be identical. The distance between these two and the distance between these two should be identical. That's between the two of them. This guy's on the low side, oscillating up and down. Eventually he gets up to the high side. And these guys are on the high side. Eventually they go to the low side as the oscillations take place. But their natural place, I guess, is on the upside, but they do oscillate up and down. They just don't travel. They don't travel to your left or to your right. I mean, it's a standing wave. Could we have found that out somewhere else? This is a little different, a little addition to some of the stuff that's on there. Could this right here be kind of telling us what's up? Yeah, I think so. Let's just quickly do that and get that out of the way for you guys. I'll tell you what I'm going to do. Is it true that K is 2 pi over lambda. Okay, we've been down this road before. Multiply by lambda on each side and divide by K. 2 pi is 2 pi. Sounds good to me. Here's K for you. I mean, I know I had a 3 here. I had a 1 here earlier. I had a 1 here earlier. I got a 3 here. Who cares? This is the K. Right there. 0.350 pi. 0.350, let's call it 0.35. Who cares? You tinker with this, that's 2 over 0.35. Multiply top and bottom by 2. Lambda equals 4 over 0.7. Aha. Lambda equals 4 over 0.7. There it is. It's all there. It all ties up. When we get comfortable with this stuff, all of it ties up. All of it ties into something. There's probably a number of mathematical tricks we can do that they're not really talking about. It's a path I don't want to take right now, guys. I think right now we need to know this. Let's not take it any further right now for our purposes. This looks pretty good, you guys, to do this. They didn't ask us that, but look at the result. Yeah, 0.5714 meter. Forgive me, 5.714 meters, and everything else we said. Okay, we'll talk to you soon. Take care.